As we know that in the spectral domain setup, if we collect the data of the image by using the CCD or the charge coupled device, then there will be some noise. Noise is inevitable, we cannot avoid the noise. But in the post-processing, we can subtract the noise. So there are various methods of subtracting noise. I will talk about them one by one. Say the first method that I will talk about is the subtraction by using the reference sum power. So there are various methods and for specific case you have to use a specific method to subtract the noise. For example, I will talk about first how can you use the reference sum signal to subtract the noise. For this method, there is a requirement that the image that we will take, there should not be any particle streak. There should not be any like this kind of particle streak. Then this method will not work. I will explain in detail why it will work and why it will not work. So no particle streak. If no particle streak, then we will be able to subtract the noise using the reference sum signal. So let's talk about little bit about how do we detect in our optical coherence tomography setup. This is a spectral domain setup. This is the laser source. We are sending light. This is beam splitter. It can be 50-50 or other beam splitters. Let's say for example we are using the 50-50 beam splitter. We are sending 50% light in this direction. This is the reference arm of our setup. Light is coming back, and also we are sending another 50% light to our sample arm. Light is hitting here and coming back, and they are basically combining in this charge coupled device or CCD camera. Now say we will image of any biological sample, and in the biological sample usually the returning light, whatever amount of light we will send, the returning light is usually 3 to 5%. So we are getting back in CCD camera very small amount of light from the sampler. Mostly we are as say this is mirror, right? So mirror is highly reflective. It is 100% reflective. So we'll get most amount of light from the reference sum here. So camera is basically detecting the light from the reference arm. So as we know that if your system is short noise limited, whatever noise you will collect, that is depends on the intensity, and so the detected photon can be converted into intensity, and intensity depends on both the sample arm part as well as the reference arm part. This is the fringe we detect. As most of the light is coming from the reference arm, so most of the component of the noise will be come from the reference arm. So one way to calculate the noise is we can block the sample arm and collect the data from the system. That means we are collecting the data from the light that's coming from the reference arm mostly, not much, not from the sample arm. Then if we generate the depth profile, say this is, say we took the data only from the reference arm by blocking the sample arm. So this depth profile is from reference arm when we block the sample arm. So we found one depth profile. So and this is our data. This is some agar data, agar sample data. So in these data we have the component of both signal that is coming from the sample arm plus noise. So we have to subtract the noise. So one way to subtract the noise is, as this is the depth profile of the reference sum noise, we can subtract this depth profile from every A lines from here. This is one A line, so we can subtract this depth profile from each A line starting from 1. So in this direction is the A line, this is the direction of depth G. So we can subtract the reference sum data from all the A lines. So this is one way to do that. But one thing is that if your system is short noise limited, so total number of noise depends on how much power the CCD is detecting. Although the biological sample is sending 3 to 5% of the light, but within this 3 to 5%, the camera is also detecting some noise. So we need to account for that amount. So if we only subtract the reference arm data, or the data that we collected by blocking the sample arm, we are not counting that amount, the amount that is contributing in the noise from the sample arm power. So one way to adjust that, say for example, what we can do is we can select a certain A line. Say for example, in the reference sum we are selecting the A line number, say 10 to 30 for example. We can select the similar region in the sample arm 10 to 30, and we can calculate the average here, average intensity. We can also calculate the average intensity here. Definitely the average intensity of the sample plus reference data will be high actually. So one thing to know, that this depth profile is generated from these data where we collected both the sample arm and the reference sum data. This will be high because here is the combination of sample arm power and the reference sum power. Now we have to ratio. Say for example, here the average value is 10, and here in the similar depth region, so here is 10th pixel to 30th pixel, here is also 10th pixel to 30th pixel. We find the average power equal to, say for example, 5. That means ratio is 2. Usually ratio is not that much. Usually ratio is say 1.1, 1% high, or only say 0.5% high, something like that. Then now whatever ratio we will find here, we have to multiply with that ratio to the depth profile to adjust for the noise that's coming from the sample arm. Then we have to multiply, we have to subtract from the image here. Now we have to subtract with the whatever reference sum depth profile, multiply by this ratio here. So we have to subtract the whole amount from each A line here. So if we do that, then we are taking care of the effect of the noise that's generating from both the sample arm and the reference arm for the short noise limited setup. So just one thing to remember is that we can do only this method when there is no vertical streak. When there is no vertical streak in the image, then we can do that, because when we are generating the reference arm depth profile, we are averaging all the airlines in this direction and generating one reference arm airline, one reference depth profile for all the 1024 airlines. So that's very important to make sure that your data has no vertical streak. If there is a vertical streak, there are other methods I will describe later on.